This is Classical Physics 2, and we're in Chapter 23, Working Problems. First problem we're going to do is number 4. Number 4, as an electron is accelerated from rest to a potential difference of 1/10 of a volt, how much greater would its final speed be if it were accelerated from 4 times as much voltage? 4 times as much voltage. That's a question. We're not doing questions, we're doing problems. Number 4, as I was saying, the work done by an external force to move a minus 9.1 microcoulomb charge from point A to point B, A to B, the work done is 7 times 10 to the minus 4th joules. If the charge was started from rest and had 2.1 times 10 to the 4th joules of kinetic energy when it's reached point B, what must be the potential difference between A and B? Okay. So I've got point A, I got point B. I go from rest to 2.1 times 10 to the minus 4th joules. Okay, so the work needed, the work that is external, plus the work that's caused by the electric field, has to equal the kinetic energy final minus the kinetic energy that I had to begin with. Now that's pretty simple to have because that's got to be 0. Okay, so the work external has to be minus Q, the voltage difference, has to equal the kinetic energy final. Okay. So the voltage difference, the voltage between B and A, has to be the work external minus the kinetic energy final divided by Q. Okay, and we know that the work done was 7.00 times 10 to the minus 4th joules, and the kinetic energy is 2.1 times 10 to the minus 4th joules, and we know what Q is, minus 9.1 times 10 to the minus 6 coulombs. That being the case, the change in voltage must be minus 53.8 volts. Okay, so that's number 4. Going on to number 10. A manufacturer claims that a carpet will not generate more than 5,000 volts in static electricity. Okay, what magnitude of charge would have to be transferred between the carpet and the shoe for there to be 5,000 volts of potential difference between the shoe and the carpet? Approximate the shoe and the carpet as a large sheet of charge separated by a distance of 1 millimeter. Okay. So we're going to use example 23 equation. Use equation 23 4b. Okay, so that's the one we're using, and we need an area of a shoe. So everybody look at their shoe and come up with an area. We're going to use 30 centimeters by 8 centimeters. But clearly it doesn't tell us what the area of the shoe is, so we could use something else. Okay, so E is equal to voltage divided by distance, which is the density of the charge divided by epsilon naught, which is Q divided by epsilon naught area. And so all that put together implies that Q is epsilon naught area voltage divided by D. Epsilon naught is 8.85 10 to the minus 12th coulombs squared per Newton meter squared. Area 0.024 meters squared. 3 times 8, put the decimal point in the right spot. Voltage 5,000 volts divided by the distance between the shoe and the carpet, 0.001 meter. And we come up with the Q is going to be 1.1 times 10 to the minus 6 coulombs. What is the magnitude of the charge that would allow this size? So that would be the magnitude of the charge. Okay, moving on. Number 16. Determine the difference in potential between 2 points that are distanced RA and RB from a very long straight wire carrying a uniform charge per unit length of lambda. Okay, so I got a wire, and it's very long, and I have lambda, which is the it's going to be in coulombs per meter. Okay, on the wire, that's fine. And I got very long wire, which is much longer than A and B. And then I got a point A, and I got a point B, and I want to know the voltage between A and B. Okay, picture's good. Alright, so from exercise 22.6, we find that for this particular situation, the E is going to be equal to 1 over 2 pi epsilon naught lambda over R. And then we're going to use equation 23-41, and we're going to say that VB minus VA the change in V is equal to minus the integral RA to RB of the electric field plus the change in I and change in I. Okay, that's going to equal minus integral RA to RB 1 over 2 pi epsilon naught lambda over R dr. And I was going to be bringing the constants to the outside. Minus lambda 2 pi epsilon naught integral RA to RB 1 over R dr. Then finally we get an integral that we can do on our own, lambda 2 pi over epsilon naught, and this is going to be natural log of RA divided by RB. And I got rid of that minus sign, that's why I can turn those guys around. And does that solve the problem? Determine the difference, yes. So that would be the voltage difference between A and B. Okay, moving on to problem number 22. A hollow spherical conductor, cylindrical, hollow, so no, it's spherical conductor has a net charge of Q. So at the center of my conductor I have a charge Q over 2. Then I have a radius 1, and I have something, and then I've got a radius 2, and there's my radius 2. And radius 2 is equal to 2 radius 1. Okay, so that's good. At the center, and the conductor has charge Q, and at the center I have a charge of Q over 2. Okay, so I have the picture correct. Okay, now with the picture correct, I need to solve for A. Write the electric field strength in all three regions. Okay, so I need the electric field strength at between, when I'm less than R2, when I'm between R1 and R2, and when I'm greater than R2. Okay. Write the electric in all three regions as a function of R. Then determine the potential as a function of R. Do the other things. Okay, well, the when I we'll do part A first. So for R less than R2 greater than R2, greater than R2. Okay, so when I'm out here greater than R2, okay, that's fine. Then the electric field is going to be 1 over 4 pi epsilon naught the Q enclosed divided by R squared, and we've done that many times before too. So that's going to be 1 over 4 pi epsilon naught 3 halves Q divided by R squared, and we would write that as 3Q over 8 pi epsilon naught R squared. Okay, then we'll look at for R1 less than R but greater than, R is greater than R1 but less than R2. So I'm inside the conductor, and inside the conductor, and I look at that, I'm in here. Alright, I'm going to say that E is going to be 0, since Q enclosed is 0. Now, do I really think that's the case? I wonder. Yeah, probably. All right, now we're going to look at for 0 is less than R is less than R1. All right, so now I'm inside the other guy, and E is going to be 1 over 4 pi epsilon naught, the Q enclosed, divided by R squared, and so that's going to be Q over 8 pi epsilon naught R squared. Okay, so that's the A part. The B part wants to know the potential when R is greater than R2. Okay, so we want to find R is greater than R2, so I'm outside the sphere again. My V is going to be 1 over 4 pi epsilon naught Q over R, and so that'd be Q total. So I'm going to have 1 over 4 pi epsilon naught 3 halves Q over R. So I'm going to end up with 3Q over 8 pi epsilon naught R. And the C part wants to know the same thing. When R1 is less than R is less than R2. And the voltage is going to be okay, now the tricky part here is that inside the conducting material there is no electric field, and therefore the voltage inside the electric field is going to be constant, and it's going to be the same as I had on the outside of the shell, because there's no electric field inside the conductor. Alright, so coming back down to here, the voltage is going to be equal to the voltage at R is equal to R2, which is going to be 3Q over 8 pi epsilon naught R2. Okay. Now, delta, the D part, we have 0 less than R less than R1. So we're going to look at E, the electric field, cross DI is equal to EDR. Voltage at R minus voltage at R1 is minus integral R1 to R. Electric field DI, which is equal to minus R1 to R, electric field DR, which is going to be minus R1 to R, 1 over 8 pi epsilon naught Q over R2 dr, which is going to be Q over 8 pi epsilon naught quantity 1 over R minus 1 over R2. Okay, so the voltage at R is going to be the voltage at R1, and those are little r's and little r1s. R1 plus Q over 8 pi epsilon naught 1 over R minus 1 over R2 and the voltage at R1 okay, where's my red ink pen? This should be R squared, not 2R, and this should be R1, not R2, and this should be R1, not R2, and this should be R1, not R2, and that one's an R, that one's an R, plus 1 over R, and then 2R1 is R2, so I would have Q over 8 pi epsilon naught times 1 over R2 minus 1 over R 1 over R. All right. Then for the E part, plot both voltage and electric field as a function of R between 0, R equal to 0 to R is equal to 2 to R. Okay. So we're going to do that. Alright, so we need a plot. And we're going to have voltage divided by voltage naught on that side, and R versus R2 on that side. And we'll go for a quarter, a half, 3/4, 1, 5 halves, 5/4, 5/4, 3 halves, 7/4, 2. So that's up to R being twice what the other guy has. And we'll go 1, 2, 3, 4, 5. And when I'm 1/2, I'm going to be at 1. And sometime we're not going to get infinitely close because that wouldn't be a good idea. And then we're going to have a straight line out to there. And then we're going to decrease as 1/R out to there. Okay, so that's the voltage. The electric field, we're going to do the same thing. We're going to have E over E naught. And we're going to have R over R2. And we're going to go with 1/4, 1/2, 3/4, 1, 5/4, 3 halves, 7/4, 2. And we'll go out 1, 2, 3, 4, 5. And at 1/4, it's going to be at 5. And at 1/2, we're going to be around 2.5. We're going to be at 0 when we're inside the material. When we get to 1, we're going to jump up to 1, and this is an exponential guy going that way. And this is exponential guy going that way, and then straight down. Okay. 22. Next problem is 26. Two charges, 3.4 microcoulombs minus 2.0 microcoulombs, are placed 5 centimeters apart on the x-axis. At what point along the x-axis is the electric field 0, and B, the potential is 0? Let V be equal to 0 at R is equal to infinity. Okay, so clearly at infinity, it's going to be equal to 0. The issue is what are the other spots that it's going to be equal to 0, because we really don't care about the spot where out at infinity, because that's just the way it is. Alright, so E is the first one is electric field, right? 26, 2 charges, the electric field. So E is proportional to 1 over R squared. And we want to know where is E equal to 0. So we want E equal to 0, which is going to be 1 over 4 pi epsilon naught Q divided by x squared minus 1 divided by 4 pi epsilon naught, the other Q, Q1, make this guy Q2, divided by the distance minus x, the quantity squared, and that's equal to 0. Okay, well, the 4 pi epsilon naughts can go away, and we can have that Q2, absolute value of Q2, x t minus x squared has to equal Q x squared. Okay, so that has to be the case. And that means that x has to equal square root of Q2 divided by the square root of Q minus Q2 times the distance. Okay, so we're going to do that, and so we'll take square root of 2 times 10 to the minus 6 coulombs, square root of 3.4 times 10 to the minus 6 coulombs minus square root of 2 times 10 to the minus 6 coulombs times 0.05 meters, and I do that and I get 0.16 meters, and then we have to interpret where this point is. So so it's going to be over here to the right, because the electric field, this guy's going that way, that guy's going this way. It would be 0 out there. So the way I do the picture, it would be to the right of the minus 2 microcoulomb charge. If I drew the picture differently and put the minus 2 guy here and the 3.4 guy there, then it'd be to the left of the 2.2 the minus 0.20 microcoulomb charge. Okay, so that's the A part. Now we're looking at the B part. We want the voltage to be different. Okay, so we want the voltage to be different, and instead of squaring it like we did the last time, we're going to go and not square the difference. So the voltage has to be 0, which is going to be 1 over 4 pi epsilon naught times Q1 d minus x1 plus Q2 d minus x1, and the 1 is interesting. All right, and then we would put those numbers in. We'd solve for x. So we'd the 1 over 4 pi epsilon naught goes away, and the other one guy goes to the other side of the equation. We then say that x1 is equal to q2d divided by q2 minus q1, and then we throw our q's in. Minus 2 times 10 to the minus 6 coulombs, 0.05 meters, divided by minus 5.4 times 10 to the minus 6 coulombs, and we come up with 0.018 meters. There's going to be 2 points, I think, where the voltage is going to be 0. So we'll have the point in the middle point occur at x1. And then we'll have another point occur on the outside at x2. Okay. So that being the case, 0.018 x1, if we allowed the first charge to be, this point to be at 0, then that first point is going to be 1.8 centimeters. So the first guy is going to happen at 1.8 centimeters, and then we're going to do it again. It's going to be 1.8 centimeters away from the positive charge. So really it's going to be like that. So it's 1.8 meters away from the negative charge going towards the positive charge. Okay, and the next point, because of the way I've drawn the picture, is going to be out this way, x2. So I'll solve it again, and this time instead of saying plus, I'm going to add the charges. So x2 is going to be q2d divided by q1 plus q2, and I'm going to end up with minus 2 times 10 to the minus 6 coulombs, 0.05 meters, divided by 1.4 times 10 to the minus 6 coulombs, and I end up at 7.1 centimeters. And this guy is going to be away from the positive charge and the negative charge, away from negative charge and positive charge. Okay, moving on to number 32. Two equal but opposite charges are separated by a distance d. Okay. Distance d, equal and positive. Equal but opposite charges, q and minus q. Separated distance d in figure 23. Okay, so A is this guy, B is that guy. No. Redraw the picture. They got a picture for us this time. So I've got positive Q. I've got a point A, distance B. I got a point B, another distance B to the minus Q charge. Okay, determine the formula for the voltage B to A, which is voltage B minus voltage A. For the points B and A on the line between the two charges as shown. Okay, so we're going to use the equations 23 2b and 23 5. That's what we're going to do. So voltage B to A, voltage B minus voltage A is going to be 1 over 4 pi epsilon naught Q D minus B minus 1 over 4 pi epsilon naught somehow I don't think these parentheses are in the right spot. Alright, there we go. Minus 1 over 4 pi epsilon naught minus Q over B. Okay, now this total distance is D. That's the total distance, D. Alright, that's the voltage at B. Okay, so we'll put parentheses there. Okay, so that's the total, that's the voltage at B. The voltage caused by the positive charge and the voltage caused by the negative charge. Okay, now we're going to find minus the voltage at A. And the voltage at A is going to be 1 over 4 pi epsilon naught Q over B plus 1 over 4 pi epsilon naught minus Q over B, D minus B. Okay, I can bring out the 4 pi epsilon naughts, 1 over 4 pi epsilon naught, and then I'd have 1 over D minus B, 1 over B, minus 1 over B, plus 1 over D minus B. Okay, and then I could go and add these guys together, and I have 2 of those guys and 2 of those guys, so I'm going to bring a 2 out, 4 pi epsilon naught, that was pretty silly, times 1 over D minus B, minus 1 over B, and do I want to find a common denominator? Yeah, I could probably find a common denominator and say that this is going to be 2BQ minus dq divided by 2. Well, I can get rid of that other 2, can't I? Well, I got to keep this 2. Okay, so I got to keep that 2. All right. 2 pi epsilon naught b d minus b. Okay, looking at number 34. Three-point charges are arranged in the corners of the square side L as shown. What is the potential at the fourth point? All right, so I've got Q, and I've got minus 2Q, and I've got plus 3Q, and I've got a point A. Okay, and I've got L, 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 and going that way I've got square root of 2L. Okay, so that's being the case. So the potential at A is going to be 1 over 4 pi epsilon naught the 3Q over L guy plus 1 over 4 pi epsilon naught the Q over the distance square root of 2L guy minus 1 over 4 pi epsilon naught Q over L, 2Q over L. Well, that looks okay. I got 3Q, I got 2Q, so I got 1 over 4 pi epsilon naught. I have Q, that's the Q over L plus Q over the square root of 2L. And my 9th grade algebra teacher doesn't want me to leave a irrational number in the denominator. So that means I've got to rationalize my denominator. So V at A, 1 over 4 pi epsilon naught, and I'd have the square root of 2Q over 2L times square root of 2 plus 1. And at that point, my 9th grade algebra teacher would like me better because I rationalized my denominator. As far as I'm concerned, there's nothing wrong with that answer. That's perfectly okay, and so is that guy there. I'm going to do number 40 next. Let's see, the charge on a rod in the figure above has a non-uniform charge density of lambda is equal to AX. Determine the potential V for points along the y-axis and points along the x-axis outside the rod. Okay, so I've got an axis and I've got this rod. Okay, that's what I've got, and I got 2L sitting there. I've got an L on one side and I got an L on the other side. Okay, and I want the, I'm looking at a point lambda is equal to AX. Okay, what we're going to do is we're going to use a small hunk of the rod, and we're going to call, and I have some point up here that we're going to come from. We're going to come from that small part of the rod. We're going to call this guy X prime, that length X prime, and we're going to call this dx prime. Okay, that small chunk. And then we're going to say my charge dq is lambda dx prime, which is going to be ax prime dx prime. Okay. I'm going to say this r up here is going to be the square root of x prime squared plus y squared. Okay, and then I'm going to say the voltage is going to be equal to 1 over 4 pi epsilon naught integral dq r . Okay, I'm going to do that. And then I'm going to say that this is going to be 1 over 4 pi epsilon naught integral from minus L to L of ax prime dx prime divided by the square root of x prime squared plus y squared. That's what I'm going to do. And then I'm going to do what every physicist always does with an integral that looks silly like that. And I'm going to say that it's equal to 0. Now, why is it equal to 0? That's a very good question. And this is a symmetry thing again. I'm going from minus L to L, and the function is even. Since the function is the answer to this is going to be an even answer, if I go minus L to L, they're going to cancel each other out, and I'm going to end up being at 0. Okay, now the other way to look at this is in the y direction. If lambda is equal to ax, that means I'm positive on this side of the rod, I'm negative on this side of the rod. How can I have any voltage up here in the y direction? I can't, because these two guys are equal and opposite. They're canceling each other out. So I can't have any voltage on the y-axis, and that's probably the easiest way to look at the problem. All right, back to the B part of the problem. I want to point on the x-axis. So I've got my rod, I got my 0 place, I've got L on this side, I've got L on that side, and I find some dx prime, some little bit in there, and I got some I have some x prime coming out to it. And I'm asking, what is the voltage out here at x? That's what I'm asking. All right, so voltage is going to be 1 over 4 pi epsilon naught integral change in Q R, which is going to be 1 over 4 pi epsilon naught integral from minus L to L of AX prime dx prime divided by x minus d minus x prime. Alright, so now we have an integral that we have to solve instead of one that we don't necessarily have to solve. So I have a over 4 pi epsilon naught integral minus L to L x prime dx prime divided by x minus x prime. I'm going to do a substitution, and I'm going to let z be x minus x prime. So z is equal to x minus x prime. And that means that x prime is equal to x minus z. Okay, and it means that dx prime is equal to minus z minus dz. Alright, now we're going to do that substitution, and we're going to say that we have a over 4 pi epsilon naught integral x plus L to x minus L x minus z minus dz divided by z. Okay, and I got a over 4 pi epsilon naught integral x minus L x plus L x over z minus 1 dz. Alright, well that's an integral. I finally got an integral that I can actually solve. So I've got a over 4 pi epsilon naught x natural log z minus z evaluated at x minus L and x plus L. Alright, so we're ready to write down our final answer. Voltage on the x-axis is going to be a over 4 at pi epsilon naught x natural log x minus L, and that's an x plus L, over x minus L minus 2L. And this is for x greater than L. Okay. Now I'm going to do 44. A metal sphere of radius r naught is equal to, I got a sphere, radius r naught 0.44 meters. Thank you very much, author, for giving it to us in meters. Carries a charge of 0.5 microcoulombs. Equal potential difference surfaces are to be drawn for 100 volt intervals. Okay, so I want 100 volt intervals. So there's 100 volts, there's a 1,000 volts, and then there's 900 volts, and then there's 800 volts as I move away. Okay, outside the sphere. Determine the radius of the first 10th and 100th equal potential surfaces. Okay, so we know that voltage naught, because of this particular thing, is going to be 1 over 4 pi epsilon naught Q over R0. And for the potential, this is the potential on the surface, Okay, so the voltage at the surface, 1 over 4 pi epsilon naught Q over that. We also know that outside, the voltage is going to be 1 over 4 pi epsilon naught Q over R, which is V naught R naught over R. Okay, outside. So now we got to find V naught. Okay, so V naught is going to be 4 pi epsilon naught, also known as K, times Q divided by R naught. So the voltage on the surface of the sphere, 10,216 volts. Okay. Now, we want 100 volt equal distance thingies. Okay. So V naught minus V is V naught minus V naught R0 over R. We want that to be 100 volt N, and we want to solve for what the N's are. Okay, so, well, we know what the N's are. The N's are 1, 100, and 10. We know that because that's what we're solving for, A, B, and C. We want to find, we're going to use that equation to solve for R. We have the R is equal to V naught divided by V naught minus 100 volts N R0. Okay, so we know that. Now it's time to solve for part A. Part A, R1 is equal to 10,216 divided by 10,216 minus 100 times 0.44 meters, and that's going to give us 0.444 meters. I'm not sure we have that many significant digits, but that's what it gives us. Part B, R2, 10,216, not R2, but R10. The 10th equidistant sphere. Who designed this problem? Divided by 10,216 minus 100 times 10 times 0.44 meters. And that's going to give us 0.49 meters. And then the C part, the 100th one, 10,216 divided by 10,216 minus 100 times 100 times 0.44 meters. And that's going to give us 21 meters away. Okay. So now we're looking at number 46. 46. A dipole moment, considered as a vector, points from the negative to a positive charge. The water molecule is what we're using. Consider the figure below. Okay, I'm considering it. Has a dipole moment which can be considered as the vector sum of two dipole moments. The distance between each hydrogen and oxygen atom is known. 0.96 times 10 to the minus 10th meters. The lines joining the center of the oxygen atom to each hydrogen has an angle of 140 degrees, okay, 104 degrees, as shown, and the net dipole moment is measured as 6.1 times 10 to the 30th coulomb meters. Determine the effective charge Q on each hydrogen atom. Determine the electric potential far from the molecule due to each dipole, and show that it is what it's being shown. Okay. The other interesting part of this particular problem is that angle, 103 degrees, changes with the temperature of water. And it gets bigger as you approach 0 degrees centigrade, and that is why water expands when it's turned into ice, and of course ice then floats, and the fact that ice floats is what allows us to be human beings, because if ice didn't float, then the oceans would freeze from the bottom up and there would never be any life on Earth. So this particular hydrogen, this particular water molecule behavior is such that it allows us to be human beings. So that's kind of cool. Okay. So I need to draw a picture. Okay, so I've got an oxygen, and I got two hydrogens. Okay, oxygen and two hydrogen, and I got an angle between them of 104, which means that this angle is 52 degrees. Okay, and okay, now the dipole moment P. So P, which is both of them, is 6.1 times 10 to the minus 30th coulomb meters. Okay, so that's this guy, P, and they're going to call this guy P1, and we're going to call this guy P2. Determine the effective charge Q on the atom. Okay. So we're going to assume that the magnitude of P1 is equal to the magnitude of P2. I think that that's implied in the problem. Then the magnitude of P1 is going to be QD, where Q is the net charge on the hydrogen atom. Okay, and D is the distance between the oxygen and the hydrogen. Okay. Now that being the case, from our picture, we can get that P has to equal 2P1 cosine 52 degrees, because there's two of them. And so that's 52 degrees. We want the x component. All right. So that being the case, we know that P1 is equal to P divided by 2 cosine 52, which has to be QD. And we can get that Q is equal to P over 2D cosine 52. And now it's time to put in numbers. 6.1 10 to the minus 30th coulomb meters divided by 2 times the distance, 9.6 angstroms, and cosine 52. Now it's going to be a little difficult to put in your calculator, but I'm sure you can figure that out. So Q is going to be 5.2 times 10 to the minus 20th coulombs. Okay. And we note that this is going to be, note that this is 0.32 times the charge on one electron. So I've got something that has a positive charge, two positive charges on it, the oxygen does, and I have two negative charges like that. This guy has 16, right? 16 positives. And but anyway, the effective charge of the hydrogen atom, of the water molecule, turns out to be 0.32 times the charge of an electron. Okay, now we're going to consider the B part. Determine the electric potential far from the molecule due to the bipolar thing shown. Okay. Okay, so I'm gonna use equation 23-7, and I'm gonna say the voltage is going to be caused by the first guy plus the voltage caused by the second guy. That's what I'm going to do. And I'm going to have 1 over 4 pi epsilon naught P1 cosine 52 degrees minus some angle theta. Let's read the problem again. Determine blah 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 shown dipole moment. Okay, so what I'm doing is I've got my hydrogen atom and I've got some angle theta sitting right there. So these guys are sitting out there. I got some angle theta sitting in there. Plus 1 over 4 pi epsilon naught P2, which is the same magnitude as P1, by the way, 52 degrees plus some angle theta. Okay, now I get out my math book to figure out the cosine formula. So I've got 1 over 4 pi epsilon naught rho P over 2 cosine of 52 okay, times cosine 52 minus theta plus cosine 52 plus theta. And then we have there's an R sitting there. 1 over 4 pi epsilon naught R P over 2 cosine 52. And this is going to be cosine 52 cosine theta plus sine 52 cosine theta. Cosine cosine plus cosine 52 cosine theta minus sine 52 sine theta. And we're going to get 1 over 4 pi epsilon naught R rho over 2 cosine 52 2 cosine 52 cosine theta. And we're going to hit the voltage is going to be 1 over 4 pi epsilon naught rho cosine theta divided by R. Okay, one more, number 50. The electric potential in a region of space varies. Okay, so V is equal to BY, A squared plus Y squared. Determine E. Okay, determine E. So, E in the X direction is, we're going to use equation 23.9. Okay, so E in the X direction is going to be minus the partial of V with respect to X. You notice there's no X's here, so that's going to be 0. We'll pick out the other low-lying fruit. The E in the Z direction is going to be minus the partial of V with respect to Z, and there's no Z in the equation, so that's going to be 0 as well. And E in the Y direction is going to be minus the partial of V with respect to Y. And now I have something I can do something with. So that's going to be BA squared plus 3BY squared. Oh, bummer, I'm dividing. Alright, so this is divided by, and so I messed up my derivative pretty bad. At least I got the first two right. Alright, so that's by divided by a squared plus y squared. So that derivative is going to be, so I want to have to think about that. So minus the derivative with respect to y of b over y divided by a squared plus y squared. Okay, well that's just the derivative of a quotient. So we can handle that. Is equal to a squared plus by squared minus by times 2y divided by a squared plus y squared squared. Alright. And so final answer is going to be y squared minus a squared times b divided by a squared plus y squared squared, but this is only in the y direction, so we have to throw in a j hat. One more to do. Number 58. An alpha particle with Q that is plus 2e has a mass of 6.64 times 10 to the minus 27th kilograms, is emitted in a radioactive decay with kinetic energy of 5.53 million electron volts. What is the speed? What is the speed? Well, we know that kinetic energy is 1/2 mv squared. So the speed has to be the square root of 2 times the kinetic energy divided by the mass. Okay, so that's what we're going to do. Velocity is equal to square root of 2 times 5.53 times 10 to the 6 electron volts times 1.6 times 10 to the minus 19 joules per electron volts, that's from the front of your book, divided by the mass of the alpha, 6.64 times 10 to the minus 27 kilograms. And we get the mass is going to be velocity of the alpha particle, 1.63 times 10 to the 7th meters per second. And that ends problems from chapter 23.